Yeah, guys, very good morning. Are you able to hear my voice?
Good morning.
Yeah.
Yes, sir.
Kalyan, still only 48 students are there. Please put a WhatsApp message to join the class.
Yes, sir. I will do.
Okay. Okay. Are you able to see my presentation mode?
Visible.
Yes, sir.
Okay. We discussed last class coupling, basic principle, and different types of coupling. In the difference of type of coupling, we discussed the sleeve coupling and this, clamp coupling. Sleeves, muff coupling and split muff coupling. We discussed the concept and the corresponding designed problem also we discussed. Today we move to the next coupling, a rigid flange coupling. Whatever we discussed yesterday, that coupling, sleeve coupling and clamp coupling, both are rigid type. Those coupling we cannot use for the, wherever shock and vibrations we can't use. Wherever alignments are necessary, due to error manufacturing input shaft and output shaft from the motor and pump, then in that places we can't use this type of couplings. So even rigid coupling, flange coupling also we can't use, because this flange coupling also under rigid coupling. But later we are going to discuss the flexible coupling. In the rigid coupling, we are going to do small modifications. That modifications will help us to flexible coupling. Flexible coupling in that sense, we can be used, it can be used for wherever vibration and shock, those places can be used. So first, now today we see this rigid, flange coupling. This is also under rigid coupling. Okay, now, before entering into this, we will see the some basic theories, and then we go for the derivation and we move to the problem. Okay, so that points I tell you, some of the points I note down. See here, flange coupling. It's also, in what is the, how what is the design here? The flange coupling here, in this flange coupling, two flanges are there. One flange is sitting on the left side of the shaft. This is input to shaft. This is output to shaft. Okay, two flanges. We are considering two flanges. One keyed in the driving shaft in the input shaft. Other is keyed with the driven shaft, output shaft in the right hand side. Okay, the two flanges are here connected by, either 6 bolt or 4 bolt or 6 bolt, 8 bolt, depends on the diameter of the shaft. We will discuss later how many bolts to be required. Here connected to 4 bolts. The two, flanges are securely connected with help of the 4 bolt here in this design. Okay, in the in the constitutive, here concentric outer circle. Anyway, one by one we discuss now. See here the power transmission, how the power is transmitted here in this system. The power is transmitted from driving shaft. See, this is the driving shaft. Input shaft is the driving shaft. From power is transmitted from driving shaft to the left side back flange. This is the left side flange, right? Left side flange through the key. The power is transmitted from driving shaft to left side flange through the key. Then left side flange to right side flange through the bolt. Then right side flange to again key to driven shaft. Such a manner the power is transmitted in the flange coupling. Okay, flange coupling. So, now this is the power transmission, order of the power transmission from input to shaft to output to shaft. So, what are the components in this coupling? Shaft, key, flange, bolt, and nuts. Okay, now these are the things, these are the components to be required to form this type of coupling system. Okay, now I mean, you see here the matting flange have this spigot and recess. I mean, even we discussed in the last DME, design of meson elements, right? In the spigot and recess type of problems and design we discussed already. The similar terminology we are using for designing this flexible, I mean, rigid flange coupling. Okay, now, I mean, see here the left side flange has the cylindrical projection. This is the left side flange has the cylindrical projection. It's called this cylindrical projection is called spigot. While the right side flange is corresponding to recess. See, I'm talking about this portion now. This left side flange, this right side flange. When we are fabricating or fixing, this should be properly positioned, this orientation. Okay, that's what here. Now this diameter must be same. Must be machined properly, then only the aligned soft properly sitting in the flange. Okay, because this is a rigid coupling. Okay, now I mean that's what I'm telling this. I mean during the assembly, the spigot fits into the rushes. The spigot fits onto the rushes of the right side flange. I mean right side flange. Okay, now I mean this is the protected type flange, protected type coupling. I mean, as I told you last class, we discussed already. I mean, unprotected flange coupling and the last. Okay, 1 minute. In the last class, we discussed unprotected flange coupling and protected flange coupling. Now, this is the see here, this is unprotected flange coupling. I told you the reason why. I mean, why unprotected coupling and protected coupling. I mean, here the revolving bolts and heads in this, just I recap again. The revolving bolt and heads and nuts, revolving bolt, head and nuts are, I mean, dangerous to the operator when this coupling is transmitting the power from driving shaft to driven shaft. Because how it will be danger for the operator. Suppose perhaps any one of the bolt or nut is getting failure, broken, then this bolt and nut in very high force will be spread on the operator body. Hence, we would like to avoid such a kind of incident. Hence, we are providing this kind of, protecting circumferential rims in the flange. Even the bolt and nuts are getting failure, then it cannot be spread in high force and it cannot be impact on the operator. Hence, we are using this kind of protecting circumferential rims, and this is the protected type flange coupling. But the design procedure both are similar. It's no different. But I mean, here this is the design procedure is similar. Both are similar, but this is little complicated the design as compared to unprotected type flange coupling. Okay, but otherwise the design procedure is same. Hence, in our discussion, only we are going to consider the protected type flange coupling only. Okay, now I come to this. Now we go for the design procedure. Now see here, now this is the protected flange coupling. In this protected flange coupling, one by one we see that. Now, I mean, what is the advantages? This type of coupling can transmit the high torque. It can be easily assembled and disassembled. Okay. And what is the disadvantage? I mean, there are many advantages you can easily understand. You just go through the book, whatever the books we referred. I mean, especially in Bandari. Okay. And see here, I mean, this is the some disadvantages. It cannot be tolerate the misalignment between the two shafts. That is one disadvantage because of rigid coupling. It can be used only wherever the motion free, I mean, vibration shock free places only able to use this type of coupling. Okay, and it requires more radial space as compared to our sleeve coupling and sleeve or muff coupling or clamp coupling. This is more space it will be required and more complicated, I mean, little complicated design as compared to muff and sleeve coupling, muff or sleeve coupling. Now, see, this is a design procedure. I mean, what is this component we discussed now? How we are designing the concept. We discuss the concept, then we go for the problem. Okay, now the rigid flange couplings are widely used for transmitting large torque. Okay. Now the flange is a protected type coupling. Here, this is the what are the important components we are saying. This one is, I mean, inner hub, central flange, and with the bolted holes. I mean, peripheral outer rims. These are the important components here. Okay. Now, I mean, see here one by one. I mean, DH. Where is the DH here? Now I erase this one. Now, if I use pointer or pen, which one is you can easily understand for explanation? Yeah, please someone reflect, because I'm this doubt I'm get yesterday onwards I'm getting. It's 1 minute. I'm using pointer to locate this where I am focusing. Suppose if I'm using pen, which one is you are comfortable? Because some students may be watching in through mobile, some students may be watching in, I mean, your laptop. So I don't know which one is better. I mean, either pen or I mean, pen or pointer. Which one is better?
Pointers.
Okay, then okay. Suppose I'm suggesting you that, guys. I mean, suppose if you are not comfortable pointer, please immediately reflect me, sir. Can you locate and point out using pen? Like that, you tell me, then I can change it. Okay. Now see here. Now DH. This is a DH. This is a hub, outside diameter of the hub. Outside diameter of the hub. Now, as per the design data book, DH is equal to 2D. And the LH, where is the LH? LH is this one. Length of the hub is 1.5 times of the diameter D. Small d is nothing but diameter. And the capital D, I mean, the pitch circle diameter of the bolts. This is the pitch circle diameter of the bolts is capital D. Okay, now, I mean, T is the thickness of the flange. This is the thickness of the flange, T. This is the T and T both are same. Now, this is the, I mean, T1, thickness of the protecting rim. Which rim we are using, the thickness is a T1. Okay. Now, DR. This is a DR. So, 1 minute. Some places I have to, this letter is not visible clearly. DR. DR. Now, this is the, I mean, diameter of the spigot and dresses. Diameter of the spigot and dresses. I mean, diameter of spigot in left hand side, it's left hand side flange. Diameter of the recess in the right hand side flange. Okay. Now, D naught, outer diameter of the flange. Outer diameter of the flange is a D naught. Here, this is a D naught. D naught. Outside the diameter of the flange. Now, I mean, here given thickness of the flange 0.5 times of diameter, thickness of the protecting rim 0.25 times of diameter, and thickness of the spigot and recess 1.5 times of diameter of the shock, and D naught is the outside diameter of the flange is 4D plus 2T1. I mean, whatever the dimensions we are discussed from the empirical relations we obtained from the design data book. Okay, now we have to remember, that's all. Okay, now suppose I want to change this kind of things, then you go for the higher studies, do research. No, D naught we can use for 5D and 3T1. You have to prove it. If you want to change, then you have to do experimental study in the laboratory as well as field study. Then we have to claim that D naught we can go for even for 3.5D plus for 3.5T1 like that. Just I'm giving the difference. I mean, just I'm giving you why we are using here, and if people who are doing research, the next stage of studies. Okay. Now, here, what is the number of that bolt and nuts we are using here? I mean, see, when n is equal to 3, the shaft diameter, suppose the shaft diameter up to 40 mm, then we can go for n is equal to 3 number of bolts. Okay, suppose the shaft diameter is 40 to 100 mm, the range, then we can go for the number of bolts is 4. And now the shaft diameter is more than 180, more than 100 to 180, then we can go for the number of bolts is 6. Sometimes it may be given such a way that, each bolts and nuts each bolt is fixed in the flange at the 60-degree was angle of difference. Then 60-degree means how many bolts? In total maybe 6. Such a way that also we may get a question in the exam. Now I come to this design concept. Now, before entering into the design concept here, this is there are two cases. The first, there are two approaches, approach 1 and approach 2 here. What is this approach? Before entering into the approach, I tell you that. The first approach, the bolts are fitted and reamed in the ground holes. Where I am talking here. Now, this bolt, I draw it here. Just for your understanding, I draw it here. Now, this bolt, right? Now, this bolt only I am draw. Right? This is the bolt head. Bolt head is always one side only, right? Right, see here. Now, the first case, the bolt holes are fitted in reamed and grounded holes. Reamed and grounded holes. This one. Reamed and grounded holes. It's very tightly fitted. This is very tightly fitted. The bolt is fitted on the holes very tight manner. Here, this is the holes. In the flange holes. Tightly fitted. Here. No gap. No clearance. Almost the diameter of the hole in the flange. Diameter of the hole in the flange almost same. Almost equal. This is very tight fit. Okay. Now, yeah, this is such a manner. Such a manner fitted here. That's what. The bolts are fitted on the reamed grounded holes. This is a grounded holes. Okay. Grounded holes. In this case, no clearance. That's what I'm telling. No clearance here. And the bolts are finger tight. The bolts are very tightly fitted. Fitted with very tight manner. Okay. Therefore, the power transmitted due to the shear resistance of the bolt. The case 1, the power transmission through the bolt due to shear resistance of the bolt. Shear resistance. Shear resistance of the bolt. Power transmission through the shear resistance of the bolt, case 1. Okay. The case 2, now case 2, I am going to explain you case 2. Now in this case 2, here this is the, the bolts are fitted large clearance holes. The bolts are fitted in the large clearance holes. Very clearance. Now, when the large clearance holes, we are applying the force on the nut here. When apply the force on the nut, then these two, the flanges, now these two flanges, because of the more clearance, the bolt entered through the holes loosely. Okay, now once entered loose, then we are using the nut on the other side to tightening the bolt. The nut is here. The nut, we are using the nut here. Now what will happen? Now the bolt, the flange, now the power is transmitted through the shear resistance between the flange. Shear resistance between the flange. That's what I am telling here. The bolts are fitted in the large clearance hole. In this case, bolts are tightened with the help of the nut. Okay, with the free loaded, tightened with the free loaded, and the power is transmitted now through the friction between the flanges. Through the friction between the flanges. This is the case 2 now. This is now case 2. Earlier case 1. Now this is the case 2. We are going to discuss now. Now give more intention now. Now first case, the bolts are fitted in the reamed and grounded holes. The force acting and individual bolts, okay, force acting individual bolts due to the transmission of the torque. See here, I mean, for our understanding, I mean, here only 4 bolts are there. Don't think about, sir, here only you are showing 4, here we are showing 6. Don't worry. For our discussing our concept, we are introducing here 4 bolt holes. Okay. Now, see here, what is this empty, I mean, torque transmission? This is the shaft while rotating. Then what is this? This is the, I mean, where is sitting our bolts, or where it is sitting? At the mean diameter. Okay. What is, I mean, D is sitting at the, D is at the sitting, I mean, pit circle diameter. Sorry, pit circle of the diameter, pit circle of the diameter, pit circle diameter of the bolt. I mean, 6 bolts are sitting here. Now, when it rotates, then first this bolt is going to be this force. I mean, obviously the opposite force, opposite bolt is going to have this force. When this force is, when this side, if it takes right hand side, left hand side, the force is going to be like this. The same opposite bolt going to be like this. Now, this is the same side. This bolt is going to be this side force. Then opposite this bolt is going to be this force direction. For, I mean, for maintaining the equilibrium, mechanical equilibrium condition, then only we are able to get the proper functioning from the coupling system. Okay. Now, what is the torque here? Mt is equal to P into D by 2 into N, because now we are using N number of bolts. Okay. Number of bolts. Now, D is a pit circle diameter. This is nothing but a P into R, I mean, P into D by 2. Now, come to this. I mean, now this is the, it should be noted that the bolts are subjected to direct shear due to the force P, the torsional direct shear. But, I mean, direct shear, not a torsional, because see here, this is a tightly fitted direct shear, not a torsional. Now, what is the direct shear? I mean, tau is equal to P into pi by 4 D square, direct formula. Use direct formula. D1 is the bolt diameter. Then once you, I mean, find this, substitute this is a P value here. What is a P? P is equal to 2 mt divided by dn. From this formula, substitute here, this is our tau. I mean, this is the, now the power is transmitted through the bolt. I mean, power is transmitted through the, I mean, with respect to the torsion, shear resistance from the bolt. Hence, we are concentrating in the shear force, shear stress in the bolt, direct shear stress in the bolt. From this equation, we are able to find out what is D1 in the later, while for going for the design. Now, I come to the second case. The bolts are fitted in the large clearance holes. What I told you now. Now bolts are fitted large clearance holes. Now we are tightening the bolt using the nut on the other side. I mean, see here. I mean, you may ask here, it may be a tight fit. For first case, I am talking now. One more point I would like to tell here. Maybe the bolt may be here tight fit, or sometimes maybe used thread also, but mostly tight fit. It's very tight fit. That's all in the first case. Second case, free holes. The other side, even tight fit, it may be you people use to bolt, nut, doesn't matter, for safer side, for safe power transmission. But When we are using loose holes, I mean the holes are with large clearance, then nut is must. Then the other side of the bolt, we are using the nut with the free loaded condition. We are applying the free load for tightening the nut and bolt. Then the flange is going to be securely fitted on the shaft. Now see here. Now the torque is transmitted. Now the torque is transmitted. Torque is transmitted. I mean transmitted from one flange to another flange. Okay, some places I use. Torque is transmitted from one flange to another flange by means of friction between the flange surface, because the flanges are tightly held. Okay, now this is uniform pressure, this uniformly distributed pressure. But this formula, please now keep in mind, I mean this is the uniformly distributed pressure concept we are going to discuss in the clutch. At that time you can understand. That time I will give you some of the explanation about this, about the friction radius, more information about friction radius. Now just you remember this formula. 2 by 3 into R naught cube minus Ri cube divided by R naught cube minus R1 Ri cube. What is R naught? R naught is nothing but outer radius of the flange D naught by 2. Outer radius of the flange, this one, D naught by 2. Okay. Now, I mean, R is the radius of recess dr by 2. Where is dr? This is dr. dr by 2. Okay. Now dr by 2. Now Pi is initial tension for each bolt. Initial tension when we apply the force here. Initial tension. Okay. Pi is the initial tension of each bolt. Now, what is the coefficient of friction? I mean, when we apply the force through the bolt and finally the fabricated the flange coupling, rigid flange coupling, then the coefficient of friction between the flanges, here. Coefficient of friction between the flanges here. Coefficient of friction between the flange surface. I mean, the coefficient of friction between the flange surface depends on material. Suppose if I am using here copper flange, the coefficient of friction between the surface, I mean friction force between the surfaces is different. Suppose if I'm as compared to steel, suppose I'm using aluminum flanges, the coefficient of friction is different. Hence, we are introducing here, I mean, the friction force with respect to this mu. The mu can be given to you because that is not our headache. Okay. Now the friction force will be. Now, what is the frictional force? Now, earlier case, this is earlier case. Now, in this case, frictional for the power transmission through the friction force between the two flanges. Hence, we would like to find out the, friction force is friction, torque is equal to mu into Pi into N into Rf. This is our friction force and the torque. Okay. Now come to this design here. This, some of the things, the flange material, they are telling that here, this is the flange material. The flanges are usually made of gray cast iron, FG200. Here the bolt, keys and shafts we are using plain carbon steels, especially rigid coupling. Flange rigid coupling. Now this is a design procedure. We are doing this. First we are discussing the concept and what is the steps to be followed for the problem. So that's what. Now the basic procedure for finding the dimensions of the rigid flange coupling. How we are finding the diameter here? Diameter here. We know how much power we are transmitting. We should know. Then P is equal to 2 pi n T by 60. From this relation, we are able to find out m torque, how much torque transmission. Then torque is tau is equal to 60 mt. This is standard calculation what we discussed earlier concept. Okay. From this, we are able to find the diameter of the shaft and the dimensions of the flange. Now this is already we discussed in the just now we have been discussed. DH is equal to the hub diameter, length of the hub, almost length of the hub also equal to length of the key. Okay, this is the mean. I mean pitch circle diameter of the bolt in the flange. Okay, this is the thickness of the flange. This is a rim thickness. Okay, this is a rod. I mean recess diameter, right? D naught is outer diameter, major diameter of the flange. Now these are the things already discussed. Now see here, the inner outer diameter of the hub, or I mean here also the hub is, I mean earlier what we discussed in the sleeve, inner diameter, outer diameter. Similarly here inner diameter, outer diameter. I mean this is the outer diameters of the hub D. Okay, and DH is DH. I mean sorry, inner and outer diameter. Inner diameter is D. Sorry, inner diameter is D is nothing but our shaft diameter. Outer diameter is nothing but DH. I mean, where I'm saying this junction I'm talking now. This junction I'm talking. This looks like sleeve coupling. This looks like, hence this is a DH. Sorry, DR or DR. This is DH. Now anyway, this is, I mean, it looks like a hollow shaft. From this hollow shaft, we would like to define our tau, the hub, how much tau is involved. Okay, now tau is equal to the mt by j into r. From this relations we are able to find out how much is torque. Okay, now very important thing, I mean this is as usual whatever we discussed earlier only, these are now only, this is very important. Now remaining things we already, the flange and the junction, at the junction of the hub is under shear while transmitting the torsional moment. Now this is very important. By dh into t. Where is by dh into t? I mean at the junction, the flange at the junction of the hub is under shear. Now at the junction, this is the junction. We are now concentrating in this junction. In this junction, while transmitting the power, so now this you just imagine it. Now I try to do in 3-dimensional in the flange, right? This portion and the junction portion subjected to shear. Then what is the area here? I mean, if you take this is a 3-dimensional view, pi d h, sorry, not this h, superscript h, subscript, sorry, here. Okay, into t, because we are this junction going subjected into shear. Hence, by dh into t, this sheared area here, sheared area is nothing but a projection area of this region. Okay, now that region I am considering now by dh into t. Okay, now what is the shear? I mean shear area, shear force. What is the shear force? By dh into t into tau. Now tau we already know. Okay, now by dh into t into tau. Okay, that is shear force. Now what is the resisting torque in this region? What is the resisting torque in this junction region? Resisting torque into dh by 2. Into dh by 2. So now this is the resisting torque at the junction. The resisting torque at the junction. Then mt is equal to, finally simplify this, mt is equal to 1 by 2 by dh squared into t into tau. Are you clear? Okay, I'm waiting. Now diameter of the bolt. Now n equal to 3. I mean this already we discussed. Okay, n is equal to 3 when the diameter is less than the 40 mm. Oh, these are the already we discussed. Now we come to the, now I mean from this whatever we discussed, this, I mean this is discussed already in this one. From this we are able to find out d1, the same formula here. Okay, now finally the tau is permissible. Now we are going to find out the, I mean, tau is permissible or not. Now one more thing, the compressive stress in the bolt can be determined by referring, I mean, can be determined. See, crushing area. Where is the crushing area? I tell you this. Now, when we apply this crushing area, I mean, each bolt. Now, when the bolt is tightly held, I mean, tightly fit on the, I mean, flange, then what is the area? This projected area we are concentrating. Now, this projected area, I mean, when the flange is, this is shearing, crushing force, no? When the flange is tightly, when the bolt is tightly inserted in this region, now this region of the flange subjected to crushing, right? What is this projected area? This diameter, you know, D1, because bolt diameter, yeah, sorry, D1. What is this? I mean, the projected area T1, T. This is when we tightly inserted the bolt. This flange is projected. This flange surface going to be crushing stress, and hence we are finding this based on crushing stress. We able to find out the, we able to design the coupling. Okay. Now D1 into T. Yeah, 1 minute. Yes, yeah, tell me, Pa. Someone is trying to ask question. So this is a D1 into T. Now how many crushing areas of, how many crushing area here? I mean number of bolts, N1, N into D1 into T. Okay. Now what is the torque? Based on that, what is the torque? Due to resisting torque, due to crushing force, due to crushing stress. I mean N1 into D1 into N into D1 into D, area of the total crushing area, into crushing stress, it will give you crushing force, then into D by 2, this is the mean, I mean pit circle diameter of the bolt, D by 2, it will give you the MT, I mean resisting torque with respect to crushing stress. Okay. Hey, are you clear? Someone is, can you mute? If you have a doubt, please go ahead. Because your mic is making noise. Okay, shall we go to problem? Yeah,
Yes,
please.
sir.
Okay, finally, here also we are using keys. In the keys, see here, the keys. I mean, once we know the diameter of the shaft and the length of the key, we can get it the key dimension from the standard table, whatever we discussed yesterday. Then only we have to identify the key stresses are, actual key stresses, actual tau and sigma c, crushing stresses and shear stresses of the keys are within permissible. The coefficient of friction between the flanges is 0.15. Mu is equal to 0.15. The bolts are made of 45C8. I mean, this is SYT. Yield strength is given 380 Newton per mm square. The factor of safety is given 3. And now they determine the diameter of the bolts. Assume the bolts are fitted in the large clearance holes. This is the case 2 now. Okay, now this is a given diameter. You have to find out the permissible tension stress, you know very well. Now come to the preloaded of the bolt. Now I mean preloaded of the bolt, second case. Okay, now before going to that, we have to find out this torque, how much torque is transmitted, because power is given here. Power is given and speed is given. From this we are able to find out how much power, how much torque is transmitted. Now, once you find the torque, then go for the, second case. This is, we are belongs to now in second case. This, okay, free holes. Now, from this, now, mean radius. Now, find out RF, friction radius. So, whatever we discuss here now, this one, friction radius RF is equal to this equation. Then substitute this. Now R naught is given. R naught is, I mean, R naught is the diameter. Diameter is given here. What is diameter here? 200 mm given. See here. And this is a dr. dr by 2 is nothing but Ri, 75. Now once we found it, the preload is, we would like to find out the preload equations also we derived earlier. Okay, preload is equal to empty by mu and rp. This is a preload. Once we know the preload, we can easily find out the diameter of this bolt. Diameter of the bolt. Now pi is equal to, I mean, preload is equal to, this is a preload we have found from the torque equation. I mean, torque based on the torque, applied torque. I mean, transmitted torque, not applied torque, transmitted torque. Now, I mean, diameter of the bolts. Once we found the pi, now pi is nothing but how much force, tensile force applied through here while tightening the bolt, preloaded. Okay. Now, pi is equal to pi by 4 into sigma d1 squared sigma t. This is a, I mean, bolt is subjected to tensile. Now from this relation, we are able to find out what is the diameter of the bolt. Diameter of the bolt is 14.2 mm. It's a very simple problem. Now I come to the second problem. Now it is required to design the rigid type of flange coupling to connect it to shaft. The input shaft transmit 37.5 kilowatt power and 180 rpm at the speed to the output shaft. I mean, through to the output shaft through the coupling. The service factor for the application is 1.5. That is, the design torque is 1.5 times of the rated torque. Okay. Select the suitable material for the various parts of the coupling. Design the coupling and specify the dimensions of the component. The simple problem only is the same problem from Bandari book, and here they have given such justification for selecting the material. How to select the material? Please go through those points. You can get it more information. I mean, I'm not those points. I'm not putting here. Please just refer your book. I mean, this how they are choosing the material. They given the justification. You can understand. Now this is a standard procedure. First, we consider the shaft. In the shaft, the permissible stresses. This is a standard procedure. Whatever we discussed, enough number of problems. How to define the permissible stresses, permissible shear stress, permissible crushing stress, permissible tensile stress. How to define? We already discussed many problems. Similarly, we define here. I mean, for shaft material, for shaft. Then second, flanges. Flanges. Now, I mean, here flanges is 16.67 Newton per mm squared shear stress. Shaft is permissible shear stress 76 Newton per mm squared. And I mean, keys. Sorry, I didn't say key. Okay, now I'm talking about key. Key and bolts are permissible shear stress is 80 Newton per mm squared. I mean, crushing stress is 240 Newton per mm squared. Okay. Now, I mean, we first we have defined the permissible stress values. Now we go to the design. Now shaft diameter. We know the power is given 37.5 kilowatt. I mean, then we know the speed. From this relation, we are able to find out the torque. Then from this torque, we are able to find out this diameter of the shaft. Okay. I mean, torque we know. Now we know the permissible shear stress of the shaft. From here, then we are able to find out the diameter of the shaft. Now, once complete the diameter of the shaft, once we know the diameter of the shaft, very, very simple to find design the dimensions of the flange, because this is empirical relations. Only you have to remember these relations. Okay, for hub diameter is equal to two times of diameter, 2 times of the shaft diameter. Length of the hub is 1.5 times of the shaft diameter, and diameter of the pitch circle diameter of the flange is 3 times of the shaft diameter, such a way that you have to, I mean, remember this empirical relations. Now, okay, now T1, I mean, this is the thickness of the flange. This is the thickness of the rim place. Okay, now, I mean, now this is a dr, diameter of the recess, 1 point in the flange. Okay, 90 mm. Now this is the outer diameter, major diameter of the flange. Okay, now from these relations, we have to find, we have found all the dimensions. Finally you have to draw based on the found, based on the dimensions, which dimensions we have discussed. Based on that you have to draw the flange, outer view of the flange in two-dimensional view. You may expect this kind of problems in the exam. Okay, now the thickness of the recess is, I mean, now the hub is treated as a hollow shaft. Now, I mean, the hub we already discussed, the hub is looks like a hollow shaft. Then we can go for this hollow shaft formula for finding the stress value. Finding the stress value, either the hub is within the permissible limit or not. The hub stress, shear stress value within the permissible limit or not. That's what we would like to verify here. Okay, so now now this is the based on this hollow shaft formula, hollow shaft concept. We have we have found that tau is equal to 16, I mean 9.38. Tau is equal to 9.38 Newton per mm squared is the actual stress, actual shear stress. I mean, this is less than the designed value. I mean, less than the permissible value. Sorry, less than the permissible value. Where is our permissible value? This one. I mean, the hub is the part of flange. You don't ask me, sir, here you are mentioning flange, how you are taking this. The hub is nothing but the part of the flange. This is a part of extension from the flange, and 16.67 Newton per mm squared. That is, I mean, whatever our actual value is less than that. Hence, this is within the permissible, within the safe limit. Okay. Now, shear stress on the flange on the junction. Now we are going to discuss about the junction. Now in the junction, 2mt divided by dh squared into t. Here also we have to verify in the junction, in the problem, in the derivation we discussed now. Here. Yeah, I come to here, sorry. In the junction, I mean, in this junction itself, in 3 dimensions we only, it can be easily, I can show you. I try to show you in the next class sometime. See here, in this junction. This is a dr. Okay. Now in this junction, I mean, we already discussed this formula. Tau is equal to 2mt divided by dh squared t. From this, we have found that okay, this is a tau at the junction of the flange is 4.4 Newton per mm squared. That also less than the permissible value. Hence, this is a safe limit. Now, one by one, can now come to this next step, diameter of the bolt. I mean, diameter of the bolt, how many, what is the diameter of the shaft here? Diameter of the shaft is 60 mm. Hence, based on our standard empirical condition, we are taking the number of bolt is 4. We already discussed, no? Number of bolt is 4. I mean, suppose less than, I mean, up to 40 mm, then we can take 3. But now more than 40 mm diameter of the shaft. Diameter of shaft is more than 40 mm. Hence, 4 number of bolts we are using. Now, this formula also we already discussed. I mean, 8mt divided by d into n tau. Now, I mean, this is the formula with respect to resisting force, with respect to the here. I come to here just for recollect information. Case 1. 8mt divided by dn into d1 square. Okay. From these relations, we are able to find out the diameter of the bolt. Diameter of the bolt. Now compressive stress on the bolt to determine compressive stress. Now, what is the compressive stress? 2mt divided by n d1t, right? Sigma c. From this is our compressive force 230. Now we are verifying the compressive stress either within the safe limit or not. What is our compressive force? Compressive stress here 240 Newton per mm square. Then our actual value is 23.03 Newton per mm square. So we are in the safe limit only. Now finally, dimensions of the key. length of the key, we from the standard empirical relation, we can find it. And based on this diameter of the shaft, we can find out the diameter of the, dimension of the key from the table. 18 into 11 mm. 18 into 11 mm key can be used. Then once we are using this type of dimension in the key, we have to verify that either, if I'm using this type, this standard dimension of the key, either my key stress limits are exceeding or not compared to permissible stress value. Hence 2mt divided by tau, this is now tau, actual tau, but our permissible value is 80, hence a safe limit. Now this is actual sigma c, our permissible value 240, hence our design is within the safe limit only. Okay, now I come to this boost type flexible coupling. Now just we discuss the concept, and the problem we may discuss in the next class. Just we discuss the concept. Okay, do you have any doubt in the earlier problem, please?
No doubt, sir.
Thank you, but thank you. Boost fin flexible coupling. See here, boost fin type flexible coupling. See, as I told you that, the rigid coupling, whatever we discussed earlier, the flange coupling, that is a rigid coupling. There are some modification we are going to do that to convert it into boost pin flexible coupling, right? See here, rigid coupling, what I told you earlier, the rigid coupling can only used for wherever, no vibration, no shock effect, right? Rigid coupling can be used only, when there is a perfect alignment between the axis and the two shafts, and also it can be used motion free from the vibration and shocks. Those places only rigid coupling possible. Now, wherever misalignments are going to happen, we are going to use this kind of jaw coupling. For example, few examples. Deflection of the shaft due to lateral force. One reason. Another reason, error in manufacturing of the shaft, error in manufacturing of the input and output shafts. Their input output shaft are actually slightly not alignment. Not proper alignment. Hence, in that place, we can go for this type of coupling, boost pin type flexible coupling. And also, wherever somewhere in thermal expansion of the power transmission system, that place also we can use boost pin type flexible coupling. Okay, now this is see here, the flexible coupling employs flexible coupling employs this flexible element. Here the flexible element we are using, the flexible element, bush, pin and brass lining, those things we are using here. 1 minute. Sorry. Right, the two flanges are now boost type flange coupling. This is similar to a rigid coupling, but we are using here fins, bush and linings. Here fin, this is a fin, a bush and lining, brass lining, lining we are using with the bolt. Then this kind of design, this kind of components, when we are adding, then the lateral and linear alignment can be easily observed by this coupling, and smoothly the power transmission can be done. Okay, but wherever shock and vibrations, then that can be also easily observed by this kind of arrangements. Bush, when we are using rubber bush, when you are using brass lining, when you are using pin along with this flange coupling, then it will become a boost pin type flexible coupling. The name itself, here we are using bush and pin and lining, lining along with the flange coupling for making flexible coupling. It's not, this is now flexible coupling. Now, I mean, one end of the pin is fixed. I mean, this is, now I am talking about this. One end of the pin is fixed with the output, fixed with the output flange or sharp with the help of the nut. With the help of the nut. The diameter of the fin is, I mean, enlarged as the input flange. Here, the diameter of the fin. Okay, this is the fin. This is the fin. Okay. Now the rubber bush is mounted over the fin. This is a fin. The rubber bush is mounted over the fin. The lining, a liner are provided in between the fin and bush. The liner is provided in between the fin and bush. Here, this is a lining. Lining surface. Lining is provided here. Brass lining. For example, this is a bush, rubber bush. This is our fin. Okay. Then we are using the right hand side nut to securely connect this fin and always simultaneously to securely hold these two flanges. Okay. Okay. Now the power transmitted from the input to shaft, this input shaft to the input to shaft. Sorry, input shaft to input flange through key. For transmission from input shaft to flange through key, right? Through key. Then power is transmitted from input flange to pin, okay? I mean, input flange to pin through the rubber bush, Again, power transmitter from input flange to fin through rubber bush and the lining surface, liner, okay? Now the pin transmits the power to output to shaft, output to flange, then output flange to key to output to shaft. This is the way of power transmission order. Okay. Now finally the power is transmitted to the output shaft through the key. Okay. Now we go for the design procedure. Now, I mean, yeah. Already I told you this. Already see here. At what cases this type of coupling it will help us. I mean, whenever lateral misalignment, we can go for this coupling. Whenever axial misalignment, we can go for this coupling. Sometimes angular misalignments also we able to use, but we cannot use such a kind of angular. Angular misalignment like universal coupling. That is where that type of place we can't use this coupling. This is a slight angular alignment, very minor angular alignment, axial alignment. Those places only we able to use. It's a large angular alignment, large intersecting place. We cannot use this coupling. Please keep in mind. Okay. Now this is a design procedure. Now I come to this. This directly come to here. Now this is a diameter of the hub to D. I mean, it's similar to whatever we discussed earlier. I mean, rigid type coupling. This, this is the hub diameter, length of the hub, diameter of the pitch circle diameter. These are similar. Okay. Now thickness of the flange and output to flange. Thickness of the output flange 0.5 D. Thickness of the protective rim here T1 is 0.25 D. And the diameter of the pin D1. This is a bigger diameter of the pin D1 here. D1 is nothing but 0.5 D divided by square root of n. 0.5 D divided by square root of n. 0.5 D divided by square root of n. Diameter of the pin. Okay. Now, I mean, this is standard empirical relations we are using for finding the 7 components. Okay, dimensions of these 7 components. Okay. Now, I mean, in the flexible coupling, it's assumed the power is transmitted with the shear resistance of the fin. Very important. Shear resistance of the fin. Okay, and I mean, as the input flange rotates, I already told you, no, the power transmission order. As the input flange rotates this side, this input flange rotates. Right, is some other color. The input flange is rotates, then input flange rotates. The force exerts a P on the rubber bush. Force exerts on the rubber bush. Okay, I mean, then the resisting force of the rubber bush. I mean, when the force P exerts on the rubber bush from the input flange, that resisting force, then the resisting force on the rubber bush going to be transmitted to the fin. Then through the fin, the force is transmitted to the outside, I mean, right hand side flange, right hand side flange. Okay, then the power is transmitted to the shaft outside, I mean, sorry, output shaft, right hand side shaft through the key. Okay, now we are going to discuss about that. I mean, see here, the resisting force
Sir,
on the rubber
hello,
bush
sir.
must be equal to the torque transmission.
Sir,
Yeah,
excuse me, sir.
tell me, ba.
The time up, sir. 11:07.
Okay, I stop it here. Just a minute. Okay, yeah, next class, only this is maybe taking derivation 10 to 15 minutes, one problem 10 minutes. Sure, 20 to 25 minutes enough. 25 to 30 minutes enough. Next class we complete, and sure we are going to start next class, next chapter. Okay, this is I mean, please go through this. I will share you this slide. Sure, I will share you this slide today, and go through this remaining concept. Suppose we straight away we go for the problem, we can save our time. Okay, we already discussed enough information. Okay, in the next class we discuss the problem. If you go through this concept, it will be very useful. You can easily understand the problem. Please do it. Okay, Kalyan, what is time now?
11:08, sir.
11:08. You tell me exact time, you give me intimation, because I am in the presentation mode. I don't know the time. That's what.
Okay.
Yeah, 78. Yeah, please, if you have any doubt, please go ahead.
No doubt, sir.
Yeah, guys, I'm kindly requesting you that I think so. You have a book also. Please go through this coupling, so we can save our time. Once you go through, you can easily understand. I don't need to explain like very in-depth manner. Okay. In the next class, we have to complete, and we have to start our next chapter. Okay, Kalyan, I'm closing the meeting. Thank you, guys.
Yes, sir. Thank you.
Please share me the attendance.
Yes, sir. I will share it.
Thank you, sir.
Thank you, Amarnath. Thank you, guys.
Thank you, sir.
Kalyan,
Yes, sir.
the results are announced or not yet announced?
Announced it, sir.
Oh, when it came?
2 days back.
Okay, okay. Okay, guys. Bye.